Okay, so in this video we're going to be looking at the simple maximization problem that we formulated last time. So quickly to go over the problem, Par Inc. is a golf bag manufacturer, and they're making two types of golf bags: standard bags and deluxe bags. So we have standard bags and deluxe bags. There are 4 departments that each bag has to go through before it is done, which is cutting and dyeing, sewing, finishing, and inspection and packaging. So those are the 4 departments, and this is how long you take in each of the departments. And we also have the total amount of time that's available based upon the labor that they have, and also the profit values for each of the bags. So with these, what we did last time was we formulated the problem. So the problem looks like this: maximize 10s plus 9d subject to these 4 constraints. And what we'll be doing in the video is we'll be solving this using the graphical method, right? So let's begin with the basics. So the very first thing that you do when you see something like this is you start with each equation. So I'm going to begin with the first inequality right here. I'm going to begin with the equation corresponding to that inequality, and we'll take it from there. So the first one is 7/10 times s plus 1 times d is equal to 630. So we always begin with the equation. So what you do is, if I plug in s is equal to 0, we are finding the endpoints, because again we'll be drawing a graph. So one axis will be the s-axis, the other axis will be the d-axis. So let's say we'll take the s-axis to be the x-axis and the d-axis to be the y-axis. So you plug in s is equal to 0, you're going to get d is equal to 630, right? And when you plug in d is equal to 0, we get d is equal to 0. We get s is equal to, so if I plug in d is equal to 0, I get 7/10 times s is 630. And I can solve that. So we can 7s is 6300, and s will be 6300 divided by 7. 7 will be 900, sorry. So 7/10, so you can multiply that and you get 900 comma 0. So that's my that's on the x-axis and that's on the y-axis, right? Okay, so those are my endpoints. So let me begin here. Okay. So this is the s-axis, this is the d-axis, right? So on the s-axis, it's 0 comma 360, then 900 comma 0. Those are my numbers. So let me say 200, 400, 600, 800, and 1000. So let's say 900 is here. So you have 900 comma 0 is one end of the straight line, and the other end of the straight line is 0 comma 630. Let's say 200, 400, and 600. Let's say 800 is here, 630 will be somewhere over there, right? So I can join these 2 points like that. Right? So that's my again, so using the same idea as before, I can say that if I take some number, so let's say that I take some number here. It doesn't have to be 0 comma 0. So let's say this point here. So there'll be 200, this point right here. So there'll be 200 comma 200. So if I plug in 200 comma 200 into the first inequality, 200 comma 200, I get 7/10 times 200, which is 140, plus 200, which is 140 plus 200, which is 340. So 340 is definitely less than 630, which means that 200 comma 200 is on the same side as on the less than or equal to side. So all the points here will be such that 7 over 10 times S plus 1 times D is less than 630, and all the points here will be the greater than or equal to. So this is the start of my feasible region. So I mean, you can either color it, or I'm just going to leave it as it is. Let's take the second point. Second line, so it'll be half of S plus 5/6 of D is equal to 600. Right? So if I plug in S is equal to 0, I get D is equal to, so I plug in S is equal to 0. 5 over 6 times D is 600. So it'll be 3600 divided by 5, which will be 720. Right? Yep, 720. So D is 720. Similarly, if I plug in D is equal to 0, so if I plug in D is equal to 0, I'll get S is equal to 1200. Maybe I should have made that scale a little bit larger. Let's see. There you go. So 0, 720 and 1200, 0. So 0, 720. So this is 200, 600, 800. So 720 will be somewhere here. And then 1200, 0. So it's 800, 1000, and then 1200. This is 0, 630. It was the previous point. And this is 0, 720. So what is interesting about this straight line is, let's do that. Excuse me. You'll notice that this straight line, the feasible region for this straight line, if you look at it, is all the points towards the origin. So these are all the points towards the origin, and all the points away from the origin will be the greater than or equal to constraint. Again, you can plug in 0, 0. It will tell you that. But all the points that are part of this feasible region and the points that are part of this feasible region will be the same as this feasible region. So basically, this constraint here does not add anything to the problem, because all points which satisfy the first constraint also satisfy the second constraint, all of them. But there are some points that don't satisfy the second constraint, that don't satisfy the first constraint, are part of the second constraint, right? So once I have this constraint, I technically don't need this one. So these constraints are called redundant constraint, and you'll see more. You'll see why in a second. Let's go through all four of them, right? Let me get another text box right here. Let's do the other two. We'll begin with 1 times S plus 2/3 times D is equal to 708, right? So if I plug it S is equal to 0, I'll get D is equal to 708 times 1.5, which is 1062, right? So 2/3 here becomes the 3/2 on the other side, so 1062. So it's simple. You plug in S is equal to 0, you get 2/3 times D. So you multiply both sides by 3, divide both sides by 2. You'll get the value of D. It will turn out to be 1062. The other option is if I plug in D is equal to 0, I get S is equal to 708, right? So it's 708, 0 and 0, 1062. So 708, 0. Sorry. 600, 800, so 708 will be somewhere over there. And the other one was 0, 1062. So this is 200, 400, 600, 800, 1000, let's say 1200 right here. So 1062 will be somewhere over there. So I'm gonna point right here, right here. I don't know why I did that. Oops. There you go. All right, so again, because it's a less than or equal to constraint with positive coefficients and positive value on the right hand side, if I take 0, 0 and plug them in here, I will get 0 is less than 708. So all the points towards the origin are my optimal solutions, are part of my feasible region. So right now my feasible region looks like this. So everything towards the origin here, everything towards the origin here, everything towards the origin here, right? Finally, let me do the final equation, which is 1/10 times S plus 1/4 times D is equal to 135. Oops. Right? So 1/10, 1/4. So if I plug in S is equal to 0, I will get D is equal to 4 times 135. So it will be 275.40. Okay. Yeah. Yep, 275.40. And if I plug in D is equal to 0, I'll get S is equal to 1350. There you go. So 0, 540, and then 1350, 0, 0, 540. So 1350, 0, 0, 540. So 400, 600. So 540 is going to be somewhere over there. And 1350, so if this is 1200, yeah. So this is 1400 right here. So 1350 is going to be somewhere over there, right? That's my straight line. Again, it's all the points towards the origin. So what is my final feasible region look like? So my final feasible region looks something like this. So color here, right here, and then right here. Oops. So this here is my feasible region. These are the points that satisfy all my constraints. Now, it turned out this way again because this is a maximization problem where all constraints are less than or equal to constraints. It is potentially possible that some constraints might be greater than or equal to constraints, in which case it won't be always the point, all the points towards the origin, right? So my endpoints are here, right here, right here, and right here. So there are 4 endpoints here. So I'm going to name them I guess I can just name them X, Y, Z, and W. Let's say W. This point is W, this point is X, this point is Y, and this point is Z. Now, just like last time, we know the value of, we know what W is, we know what Z is, but we don't know X and Y, and we're going to have to calculate them, right? So you get W, X, Y, and Z. So those are the 4 points, right? So let's write down the points. So 0, 540 for the first one. So 0, 540, right? And Z is 708, 0. So we need to find points X and Y. So X is the point of intersection of these two lines right here. So how do we know which lines these are? So we know what the endpoints are. So this is this right here was the first straight line that we drew, and this right here is the last straight line that we drew. This is 1350 right here. Let me get 1350. This is 1350, 0. Right. So X is the point of intersection of the very first line, so which is 0, 630 and 708, 0. That's the first line. So that's the cutting and dyeing straight line, and the last line is inspection and packaging straight line, right? So that's the those are the 2 points of intersection here. Now this point of intersection is again this is 0, 900 and so again, so this is the first straight line again, and the third straight line. Now, one thing I wanted to notice is that this constraint that we had here, which was the second constraint, the sewing constraint, is really not a constraint, because if I take the eraser and I remove this constraint, it doesn't affect the feasible region at all. The feasible region is not touched. So this constraint is called a redundant constraint. It's redundant. Good. Anyway. So this is a redundant constraint, because whether we have the constraint or not, it doesn't affect the feasible region. Okay, so let's find the points X and Y. Right, so I'm going to find the points of intersection. There are going to be 2 here. First, let's find point X. Right. So which is the point of intersection of the first straight line, 7/10 times S plus 1 times D is equal to 630. And the final straight line, which is 1/10 times S plus 1/4 times D is equal to 135. So we have a couple of options here. We can either make the coefficient of S the same, or we can make the coefficient of D the same. To make the coefficient of S the same, we'd have to multiply this whole equation by 7 and then subtract. To make the coefficient of D the same, we have to multiply the second equation by 4 and then subtract. So let's get rid of the S, right? So I'm going to multiply this whole equation with -7 and multiply with 7 and subtract, however you want to look at it. Fine. That is what I'm going to do. Okay, so what this does is you cancel out the 7 over 10 and the 7 over 10. Then you have 1 times d minus 7 over 4 times d. So 1 minus 7 over 4, there'll be minus 3 over 4 times d is equal to 630 minus 7 times 135. So 630 minus 7 times 135 is negative 315. Right? And this I can solve for d. So negative and negative, the negative signs get cancelled. So I multiply by 4 and divide by 3. That will be 315 multiplied by 4 divided by 3. That will give me 420. It's a good number. Right? So that's the value of d. D is 420. So that's the point of intersection. So I can plug it into the first equation. So if I take the first equation and plug it in, I get 7 over 10 times s plus 1 times d, which is 420, is equal to 630, right? And so this says 7 over 10 times s is equal to 630 minus 420, right? Which is 210. So I can multiply by 10 on both sides, divide by 7 on both sides. That'll give me s is equal to multiply by 10, 2100, 300. So this point is s is 300, d is 420. Right here. Yeah. S is 300, d is 420. Right? So 300 comma 420, that's the first, that's the point x. Now let's find the point y. Similarly, the point y. So to find the point y, oops, draw. So we'll go through the same exercise, but this time it is 7 over 10s plus 5 over 6 times d is, oh, I'm sorry, 7 over 10s plus 1 times d. So 1 times d is 630, and the finishing constraint, which is 1 times s plus 2/3 times d is equal to 708. So again, let's make sure this is correct. So if I go back to the beautiful figure that I have, so this is the point of intersection. So one of the straight line that passes through it as 708 comma 0, and the other end is, if I remember, 1062. So let me make sure I write that here. This is 0 comma 1062. And that is this straight line here, the finishing straight line. Straight line corresponds to the finishing constraint. And the other one is 900 comma 0 and 0 comma 630, which is the first one, which is my cutting and dyeing constraint. So you'll notice that there are multiple points of it. There is this point of intersection here. There is this point of intersection here, which we are not going to consider. And there is this point of intersection here. They're all points of intersection. We're not going to find all of them. We're only going to find the ones that bound our feasible region. Right? Right. So let's solve this quickly. right? So how do I do this? So again, couple of ways. I can either multiply this with 7, 10 and then subtract, or I can multiply this with 1.5 and then subtract. Either way, it's okay. No, just to make my life easier. That work better? No, it's fine. So I'm going to multiply the second equation, the whole equation, by 7 over 10 and subtract. Yeah. Right. So I'm going to multiply the whole equation with 7 over 10. So I'm going to take this equation, 1s plus 2/3 d equal to 708, multiply both sides by 7 over 10, and then subtract. The reason is I want to get rid of the s. So that gets rid of the s. Then solve for d. So it'll be 1 times d on the top, and here it'll be minus 7 over 30, right? So 1 times d minus 7 over 30, that'll be 23 over 30. So, no, that's 14 times. 1 times d minus, yeah, minus 14 over 30. So that makes it 16 over 30. Yeah, that makes more sense. So it's negative. So it's 16 over 30, not negative, straight up. 16 over 30 times d is equal to 7 over 10 times 708. Wow. 495.6. I can solve for d. So d will be, so 495.6. I'm going to multiply that with 30, then divide by 16. Okay, I messed up somewhere. 7 over 10, 2 times 3, 7 times 2 is 14, 3 times. Right, obviously. So I didn't do the 630 minus that. Okay, so okay, for a second I was so 708 times 7 over 10, that's 495.6, but that 495.6 is subtracted from 630, so it'll be 630 minus 495.6, 134.4, right? So it'll be 134.4. Yeah, so that makes sense. So 134.4 times 30 divided by 16 is 252. So d is equal to 252. So I know that the final solution here will all turn out to be integers because of the way the numbers are. So this kind of makes sense. That's why I was mystified for a second. 252. So d is 252. So I can plug it into the equation and find the value for s. So I can plug in d is equal to 252 into the first equation. We get 7 over 10 times s is equal to plus d, which is 252, is equal to 630. So if I solve for s, so 630 minus 252 is 378. Multiply by 10, divide by 7. Oops. It's 378. Times 10 divided by 7 will give us 540. So, yeah. So again, I mean, this algebra y'all can do yourself. So it's d is 252, s is 540. So it's 540 comma 252. There you go, 540, 252. There you go. So now we can find the value of the objective function. The objective function is 10 times s plus 9 times d. So let's find all of these numbers. So if I plug in 0, 540, so it'll be 0 times 9 times 540 will be 4860, right? 4860. So 9 times 540. If you plug in 300, 420, $6,780. $7,668. Finally 708, 0. That's times 10, so I can just do 7,080. There you go. So these were the profit value. So if you don't make any regular bags and make only deluxe bags, you'll make a profit of 4,860. If you just make standard bags and don't make any deluxe bags, then you'll make a profit of 7,080. If you make 300 regular bags, 420 deluxe bags, you'll make a profit of 6,780. If you make 540 regular bags, 252 deluxe bags, you'll make a profit of 7,668. And this is clearly the highest profit. So this here is the optimal solution right here. So what is the optimal solution? So the optimal solution is make 540 regular standard bags, make 252 deluxe bags, and that will give us a profit of 7,668. And no other solution that satisfies all your constraints will give you a higher profit. That is the maximum profit that you can make, 7,668, and you make that with this combination of standard and deluxe bags. Right? That's the graphical solution. So again, I'm going to end this here. Take care.